We have a circuit with several loops and branches, 4 different resistors and 2 EMF sources. Now most of the variables are given and I have them listed underneath the circuit, and 4 of the variables are unknown. I circled them on the picture, and we are going to calculate these unknown quantities. First, let's start by calculating I3. That is the current on resistor R3 in the middle branch. So for that one, we are going to apply Kirchhoff's junction rule. Let's focus on this junction right here. I'm going to call this junction junction A and apply Kirchhoff's junction rule at this point. Junction rule says sum of the currents going into a junction will be equal to the sum of the currents going out of the junction. When we look at the picture, all of these 3 currents, I2, I3, and I4, all of them are going into junction A. Therefore, we get I2 plus I3 plus I4 equals 0. Let's isolate and solve for I3. We get I3 equals negative 7 amps. What does it mean to get a negative current? It just simply means that my original assumption for I3's direction was wrong. In the picture, I have I3 pointing down the middle branch, but because I got a negative result, that means that was wrong, and I3 in reality is pointing up in the middle branch, so it's going out of the junction A. Next, we will look for the unknown EMFs, EMF1 and EMF2. Note that I have modified my picture. Now in my picture, I3 is pointing up. I have also included I3 in my list of known quantities, now with a positive sign because I have the direction of the current correctly shown in my picture. To find EMF1, we are going to apply Kirchhoff's loop rule, starting from point A, going in the counterclockwise direction around the lower left loop. So starting from point A, I'm traveling upward in the middle branch. The first circuit element that I cross is R3. I'm also going in the direction of the current, which is pointing up. So that's a potential drop. So the potential change as I go from the bottom of R3 to the top terminal of R3 is equal to negative I3 R3. Next, I turn left and I cross the EMF1 from its negative terminal towards its positive terminal. That's an increase in potential. So therefore, the potential change is going to be plus EMF1. Then I turn down on the left-hand side branch and I cross the resistor R2. I'm going in the same direction as the current I2. Again, that is a decrease in potential, so the potential change is equal to negative I2 times R2. After resistance R2, I move along the bottom branch from left to right, and there's nothing, no more circuit element until I get back to point A. So that's all we have. We set this equal to 0. Now let's isolate EMF1 and calculate its numerical value. We get EMF1 equals 34 volts. Now, how do we find EMF2? Well, exactly the same way. Let's start from point A again. This time, let's go in the clockwise direction around the lower right loop so that we're including EMF2 in our loop. And let's set up our Kirchhoff's loop equation. Note that I have slightly modified my picture. I have switched the terminals of EMF2. Now, starting from point A, I go up, I cross the resistor R3 in the direction of the current I3, so that's a decrease in potential. By how much? By I3 times R3, so I start with negative I3 times R3. Then I turn right and I cross the EMF2 from its negative terminal to its positive terminal. So that's an increase in potential, so that will be plus EMF2 in my equation. And then I turn down towards I4 and I'm following the current I4. So again, that's a decrease in potential, and the potential change is equal to negative I4 times R4, and at the bottom branch I go from right to left. Now there's nothing, no more circuit elements until I get back to point A, so that's the end of my loop. I set this equal to 0. When we isolate EMF2 and substitute the numerical values, we get EMF2 equals 20 volts. Finally, we are going to calculate R1, again applying Kirchhoff's loop rule. Now again, one more modification I made in my picture. I1 originally was pointing in the wrong direction. It should be pointing to the right, so I corrected that as well. So applying Kirchhoff's loop rule to find R1. Now which loop should we use, right? Well, it turns out you can pick any loop that you want as long as it includes R1. Now I decided to use the top loop. I'm going to start from point B and I'm going to travel in a counterclockwise direction around the top loop. Starting from point B, traveling left, the first circuit element that I see is R1, and I'm going against the current I1, so that's an increase in potential. And the potential difference as I go from the right-hand side terminal of R1 to its left-hand side terminal is equal to plus I1 times R1 using Ohm's law. Then I turn down on the left-hand side branch. There's nothing. I turn towards EMF1. I cross EMF1 from its positive terminal towards its negative terminal. That's a decrease in potential, and the potential changes minus EMF1. Next, I cross EMF2 from its negative terminal towards its positive terminal this time. So that's an increase in potential, and the potential difference is plus EMF2. Then I turn up on the right hand side branch all the way to point B. There's nothing in between, and that's the end of my loop. I set this equal to 0. Let's isolate R1 from our equation and calculate its numerical value. And here's our result after the algebra and numerical substitution. R1 equals 3.5 ohms.